dear student, let us begin the lectures on machine design part 1. This is lecture number 13 and today's topic is design of fasteners. This is the first part of the lectures on that topic. Now in the last few lectures you have learned the general principles of machine design, that is how to design a machine element. Now the design has various aspects, and in this course we are studying only the strength aspects of design. While designing an element, we have to make the dimensions properly such that it can sustain some load. Now the way to design is to check against different failures. So there are various failure criteria which you were taught in the last few classes. Then the strength of the element depends on the type of loading. If the loading is static loading, then of course the material may fail either because of a large tensile stress or a shear stress. Now if the material is a brittle material, then the failure is due to the large tensile stress, and there is the corresponding failure theory that the principal stress, which is the maximum stress, tensile stress available at a point, should exceed a certain value if it fails. Similarly, if the material is a ductile material, then the failure is predominantly because of shear. There we have two theories of failure. One is if the shear stress is beyond certain limit, then the material may fail, or what is known as the von Mises theory of failure, where it says the strain energy, the deviatory strain energy, that is the distortion strain energy, should exceed certain limit, then only the material fails. If the loading is, on the other hand, a variable loading, that is a dynamic loading which fluctuates with time, then the failure criteria is completely different. If it is purely fluctuating, that is, if there is the mean stress is 0, then the material fails if the stress exceeds the endurance limit, that is the amplitude of the stress exceeds the endurance limit. Now in all the design procedures we have to make the design safe against various other uncertainties. You will notice that in designing an element there are a lot of factors which are uncertain, that is we cannot model them, and those uncertain factors may not affect the designing process. So in order to do that, we will have to make a large safety margin, and this safety margin is provided by taking a factor of safety. These were all taught in the last few classes. Now from now onwards we are going to use those theories of failure as well as different other property and different other criteria in order to design few machine elements. Now today's lecture will be on the design of fasteners. Now fasteners, they are very important member in a machine or in a machine component, because a machine which may be a huge structure, it cannot be fabricated or manufactured as a single piece. So we'll have to make different components and then tighten them or join them together to make a complete whole. Take for example a gearbox which has a number of gears as well as shafts and various other things. Now that cannot be designed, that cannot be manufactured as a single entity. So we make instead number of gears, number of shafts, etc., and then assemble them. So in this assembling process we need the elements which will join one part to the other. So if the fasteners, that is the joining elements, are weak, then whatever be the or how strong the design of the members may be, the material will or the machine will not serve its purpose because the joint will fail. Therefore the joints are one of the very important members in a design. We start this design with the design aspects of joints because these are relatively simple, and in today's class we are going to learn how to use those theories of failure effectively in order to join a very simple fastener known as the pin type joint. So let us now look at different types of joints first. We have here the classification of joints. We have non-permanent joints. The joints are mainly of two types. The joints where the members are connected such a way that they could be dismantled or disconnected according to our will. So without damaging the components, we can disconnect those two components. There are various joints available which are non-permanent type. One is the bolted joint. Bolt, it looks like all of you know. So there are threaded members. This we will learn under the heading of threaded fasteners. This is also a fasteners, but this is known as a threaded fasteners. Then we have rivets. Rivets, they look like bolt, but they are long rods which connect two parts. Suppose there are two plates which we are going to connect. This is one plate and this is other plate. So this is one plate and this is the other plate. Then the riveted joint looks like somewhat this. So this is the riveted joint where this is a single piece. This one is a single piece. So this is a riveted joints. Then we have keys. We shall spend some time talking about the keys. There are various kinds of keys known as sunk keys, feather keys, taper keys, etc. Couplings are normally used to join two shafts axially, and the couplings, the joints should be a little flexible. We will study all about that in due course, but these are the few types of the non-permanent joints. Permanent joints are those joints, on the other hand, which is such that the two components which are joined cannot be dismantled without damaging one of them or both of them. So this is a component which is permanent, as the name suggests. There are various examples. One is welded joint. All of you know what is welding. Then soldered joint or braced joint there are. Then adhesives. Now industrial adhesives are being used today in various parts. So lots of researches are going on, and still new polymers are fabricated which serve different purposes for adhesives. So this is ongoing process going on. The main point is that the joints are so important that every time we want to find out new kinds of joints which are effective, which will not weaken the machine elements by being itself quite weak. So joints are that way important. In today's lecture we are going to study some how to design a pin joint. So let us now go to design of pin joints. Now there are different kinds of pin joints. We take a very simple example of joint which is knuckle joint. Let me draw first and then we can explain. So knuckle joint, it has two parts. One is so this is one part which has hole in it, Now this is a rod, this is a circular cross section, this part, and if you look from top it looks somewhat like this. This is octagonal shape, and there is a hole out there. So this is one part, and we are going to connect this is continuous rod which has some diameter d, and this is connected to the other member like this. This is another part which has again hole in it. So look from above, it will look something like this. This is again has the same hole, and through this we insert one pin. This is a pin where this part, this is known as the collar of the pin. So this is pin, and this is the collar of this pin, and this is a split pin, that is we insert a pin over here, there is a collar, and we fixed this pin with this arrangement, with this nut kind of thing, by means of a split pin. We insert the split pin through a hole here and then fix it. So this is what is known as a knuckle joint. So let me erase the bottom part and explain the purpose of this knuckle joint. So here what we see here, this is a joint. Now there are two rods which are connected together. Now normally we apply two forces. So this joint, it takes a large tensile stress. What happens when we apply a tension here? So this pin arrests the motion of this part 1. This, let us call this is part 1, and let us call this part 2. So it arrests this part 1, and this part arrests the motion of part 2. So this is the purpose of this pin. Now you see that these two rods can rotate. If you remember the top view, then it can rotate freely about this axis. So this joint cannot take normally a compressive stress. It can take large tensile stress, it cannot take much compressive stress, because this is flexible, so it can rotate. So once we apply compressive stress here, then it will just buckle. If you let me call it buckling, so it will just buckle. But if this pin is guided properly, then it can really take some compressive load. Now this kind of joints are used very often in the bicycle chain. You have seen this kind of pin joint. Sometimes we used in the tie rod in the roof truss. Valve rod and various other purposes. So this is very commonly used joint. Now here we want to design such joint. So the design criteria may be various, we are going to discuss them. Suppose this load P is given, so we want to design this joint such that it can take some load. Now let us go to the design and see how this could be done. Now first of all, we have learned various criteria of various failure theories, and we are going to use them. Now when the P is larger than some value, then there may be various kinds of failure. One is that if P is really large, then this tie rod or this rod could be broken. So, or this one may be broken. Now then if you want to apply the theory of failure, then you will have to take a cut across these sections. So if you take a cut there, then a pressure P is force P is acting, so definitely normal force P is there. So the stress will be now, normal stress is P divided by the area pi by 4 d square, if d is the diameter of this rod, and this sigma should not exceed certain limit. So this sigma must be less than sigma allowable. What is sigma allowable? Sigma allowable will be equal to sigma ultimate divided by some factor of safety. So if the factor of safety is more, then of course sigma allowable is less, and for that, for a given P, we will have to increase the value of D. So if you take a large factor of safety, then the dimension becomes larger. So with the increasing dimensions, there will be lots of other factor coming into play, that is the weight of the joint may be high, or the material cost incurred may be more. So we will have to compromise, we will have to find out what is the correct factor of safety. This are done, well, the factor of safety usually this is taken from the previous experiences, and they are different for different manufacturers. They could be obtained from the design handbook as well. So there are various guidelines for them, but the fact is we have to find out what is this factor of, we have to first select what is the factor of safety. Ultimate stress, this is tabulated. We will have to select the material. Material selection is one of the very important thing in design. First of all, we will have to select proper material. Then material selection depends on various other factors, the environmental conditions, the temperature, etc., etc. So when the material is properly selected, then sigma u, it could be looked from the table, and factor of safety is selected. We choose the factor of safety. Now in this formula, what we know? We know this P, and we know the sigma allowable. So from this we find out what is the smallest D required. Now sometimes in the design procedure, here of course it is not so. Sometimes we have already designed the value of D. We have found the value of D, and we know this P. So we want to check for safety. Now if this is satisfied, then we can say that this is quite safe. So this is how the diameter has to be selected from the given informations about P and sigma allowable. Now about the other parts, we will have to break them into different components. First of all, let us see the component number 1. So if you draw the component number 1, then what you see is so this is component number 1, and we have this force, applied force here. Definitely this force will be balanced by this contact force between the pin and member 1, and therefore there will be a contact force here. What is the distribution of the contact force? We shall come later, but but if there is a clearance, then of course there will be no contact pressure on here, but there will be a large contact force on this side, on the left hand side. So now we will have to see what are the critical sections, that is what are the first modes of failure, which way the material can fail, and those are the critical sections, and we will have to design the dimensions so that the critical section does not fail. Now first of all, once we see this, then obviously the material may fail also in tear. So it may so happen that it fails by breaking from this. So we have to now design these diameters, etc. Now if this length is, this thickness is T, let us say this much is T. So this diameter D1 and D2, let us take this is D1, the inner diameter is D1, and let us take this as D2. Okay. So we have to design this D1, D2. Now once we know that this is a critical sections, then we will have to draw the free body diagram, or draw the internal forces developed in that critical sections. So the free body diagram will look like, so this is the part, and here of course we get this force. So the total force is P. So this is roughly, you can take P by 2, P by 2. So total force is P. So therefore the average stress here will be, along this section the average stress will be P divided by the total area. Area is T, T is the thickness, and times this distance, which is equal to D1 D2 minus D1. So this will be the stress developed, and for designing the thickness or D2 minus D1 etc., we need to satisfy this expressions, that is P allowable divided by T times D2 minus D1. This is the normal force, it should be less than sigma allowable. So this condition has to be satisfied. Now once we know that, then we can design what is the value of D1 or D2 if T is properly chosen. So this is one way of failure, and we have one expression here. Now what is the other way of failure? Let us look at the, again the same since there is pressure over here on this region. So the material may also tear away, that is this part, if the load is too high, then this can come over here. So it can just tear away. So when it tears away, then of course this is one such critical section, it just goes away. Normally it should not go like go straight, it may go in a radial way also. So but we can design roughly based on this this mode of failure. So let us consider the free body diagram of this part. Free body diagram of the part will be now So here we have this one. Now the shear stress, now here it will be, you will have P by 2, P by 2. So then the material fails under shear. So it, because the force is a shear force, so we'll have to calculate for the shear stress. Then the next step is to calculate the shear stress, and this shear stress will be equal to P by 2 divided by, this is the average shear stress, this is divided by this length, and this length, although it may look complicated, but roughly this length, that is making some approximations, this length could be taken as the same, that is this one can be taken to be the radial length, which is equal to d2 minus d1 by 2 and times T. So this is the shear stress. So this shear stress must be less than allowable shear. So this has to be satisfied, and once this is satisfied, then it will not fail in these configurations. So this is one such failure theory. We have used again the failure theory, that is this material breaks for maximum shear. What is the other way of failure? Let us look at them in somewhat clear form. Again, let us draw so now if this pressure, here is the pressure acting, if the pressure is too large, then this surface gets damaged. So although it does not fail completely, but there may be elongation here. So the pin shifts here by damaging this surface. So that has to be checked, because if this is damaged, then of course the material gets weakened, and there is a tendency for further propagation of different cracks and failure, ultimately leading to the failure of the entire joint. So what is that bearing stress? This is known as the bearing stress, that is stress developed due to the contact. What is that bearing stress? That clearly depends on the pressure profile developed here. So here we do not know exactly what is the pressure profile developed. We have to make some judicious assumptions, and there are few assumptions. There are two assumptions which could be made. For example, if you take the large, okay, the hole over here, that is this part, then the pressure may be distributed such that this is, let us say, maximum is Q naught. So the distribution may be a cosine functions. If you measure theta from here, theta from this direction, so Q theta may be equal to Q naught cosine theta. So this is one such distribution. So there may be another distribution, that Q theta is independent of Q of theta. So Q theta is a constant. So this is uniform pressure distributions. Now if you take this kind of pressure distribution, then what will be, if you what will be the value of Q naught? Because we have to satisfy again the force balance equations. So if the force balance equation is taken, so the entire the summation of this force, that is the total force, this is distributed, hence the total force will be equal to P. So if you take that into account, and then you can write down the force balance equation. That is, if you take a small area here at angular distance theta, so we get the total force acting is q theta times r, or d1 by 2 d theta. So q naught d1 by 2 d theta times t, I'm sorry, this is q theta so this is the force developed on this surface, and this acts at an angle theta. So therefore the horizontal component will be this times cosine theta, and we'll have to integrate from minus pi by 2 to pi by 2, and that must be equal to your given pressure P. So from this relation we can find out, now you substitute in place of q theta this expressions q naught cosine theta. So therefore it becomes d1 by 2 times t. So this becomes d1 by 2 times t q naught and cosine square theta from minus in pi by 2 to pi by 2, and this becomes pi by 2. So therefore what you get after that, if you just do that, then it becomes ultimately q naught is equal to 4 by pi P divided by d1 T. So this is the maximum pressure developed here. Now this is the again the maximum pressure, and this must be less than SC, that is the crushing strength of this material. So the material may be crushed, so q naught may be less than SC. But this is very complicated assumptions, but one simple assumptions could be that q naught is a constant. Q naught is constant and q theta is constant, again equal to q naught. So therefore we have, in the second assumptions, we have the this following case, that is pressure is uniformly distributed. In that case, if you do the same analysis, then you can find out this is nothing but, we can have this following expressions, that is q naught is equal to q naught times the total area, which is equal to d1 times t is equal to p. So therefore q naught will be equal to p divided by d1 t equal to p divided by d1 t. So therefore you see that if you use this, let us say that this is based on uniform pressure theory, uniform pressure. So in the uniform pressure theory we have the q naught, which is a little lesser than that. Here this is multiplied by a factor 4 by pi, which is greater than 1. So therefore we have more pressure over here. So therefore if you design with this, then we have a conservative design, that is now we have Q naught is more than this value. So if you want to have a design, if you want to make the select the value of D, if you use this, then you get a larger value. But nevertheless, normally we use, because we want a very simple design, not very complicated, because we should not we want some answers in the simplest way. So therefore we design based on this second assumptions, and here and in future also, when we want to find out this crushing strength, then normally we use this uniform pressure assumptions. So in this uniform pressure assumptions, we have this following expressions. Now the strength criteria based on that is again P divided by the total area, that is D times D1 times T, this is the projected area, and this must be less than SC. This is the crushing strength. Now the crushing strength is more than definitely the tensile strength, because the material is very tough against crushing. So this is another again one formula which is to be used to check the safety of the design of this I bar. Now these are the three things which one has to consider while designing this I bar. Now the next important thing is the pin. Now we'll have to see what are the different modes of failure of a pin. So here let us see the pin. So this is the pin part. We have a collar here, and this is again the bottom part, which is a ring. Now this part, so therefore this part is connected to this fork end, and this part, the middle part, is connected to the to this I bar end. So we have a different kinds of force pressure distributions on this pin. Again we will have to make various assumptions. The first simple assumption is that the force is uniformly distributed. So here the pressure is, the total force acting is P by 2, here the total force acting is P, and again here the total force acting is P by 2. So now this is one very simple assumption, and we have to check against failure. Now you see, this is just like a beam which is subjected to transverse force. So we can draw various things like the shear force diagram. If you draw the shear force diagram, let me draw the shear force diagram. Vx, and x is the length along this pin. So let us measure this length x here. So the shear force diagram will look like, so there will be this one, and then it starts increasing, and it reaches maximum over here, and then it decreases. So this value is P by 2, and this value is P by 2. Again we can have bending moment diagram as well, but let us now ignore this bending moment for the first time and see how does it fail. So since the shear force is P by 2, maximum shear force is P by 2, and it appears in this sections, so therefore the shear stress, the average shear stress, can be taken to be tau is equal to P by 2 divided by the area of cross section, which is equal to pi by 4 dP square. So, this is the shear stress developed. Now, again we know from the basic theory of Euler beam that the exact distribution of shear stress is not the average, but the maximum shear stress occurs somewhere in the neutral section, on the neutral plane, and this is roughly for a rectangular bar. It is roughly about 1.5 times the average value, the maximum shear stress. But for a circular cross sections, we have something different. We have to use the formula that tau is equal to V. We'll have to use this formula, where if you want to use a precise, we'll have to use precisely the form for the shear stress, then tau is equal to V times Q divided by I T, where I is the second moment of area of the cross section and Q is that section, this is the first moment about some area which you know of course, then V is the total shear force and T is the thickness of that particular sections. So, this gives more exact result, but for preliminary calculations we can of course use the average value tau average, which is equal to V by A, which is for this case is P by 2 pi by 4 d pin square. Now, T average, if you use this formula, T average must be lesser than some value and we have to calculate dP from it. So, this is one way of calculating, but there are further complications here. We have ignored the bending moment. Now, there is always some clearance between the pin and this I bar or the fork end. So, therefore, there is a tendency that it will bend and it bends something. If this part is, so it bends like this. So, we can draw the bending moment diagram and see what is the effect of this bending stress. Now, if you draw the bending moment diagram, again the same axis, then if you remember the earlier drawing for the shear force, then the bending moment diagram looks somewhat like this. So, this is the bending moment diagram and the maximum bending moment occurs over here. And what is the value of maximum bending moment? That maximum bending moment of course will be equal to P by 2, here this force is P by 2 times this distance minus P, again P by 2 here times this small distance. So, you can calculate this knowing this few distances. One is this distance, let us say T1, another is distance from this point to this midpoint or this sections. So, we can find out what is this M max over here. Now, once this M max is found out from this chosen distribution, then we can find out the bending stress. The bending stress formula is very well known, that sigma bending is equal to M y by I, where y is the distance from distance of any point from the neutral axis and I is the second moment of area. Now, if you take the circular cross section, then of course the y by I by the maximum value of this bending stress. Now, this has the maximum value. The maximum value will be equal to M by Z, where Z is equal to pi by 32 d cube. So, if you use this formula, then we can find out maximum bending stress, and this maximum bending stress must be less than sigma allowable. Now, this is not the end, because here where the maximum bending stress occurs, the shear stress is 0, but there may be other sections where the shear stress and bending stress are simultaneously present. For example, take these sections along this. We had the maximum shear stress. If you look the shear force diagram, if you look at the shear force diagram, this was roughly the shear force diagram and the bending moment diagram. So, this is Vx, this is Mx, positive here. So, X. So, you see that here bending moment is maximum, but shear force is 0 in the mid plane. But here we have definite some value of shear force as well as bending moment. Once we have that, then we have both the normal stress and the shear stress. Then we will have to use other theory of failures. If the material is a brittle material, then of course we will have to find out the maximum principal stress, and the maximum principal stress, if there are then the maximum principal stress is given by this form. It is sigma max, sigma 1 is equal to sigma x by 2 plus sigma x by 2 square plus tau square. So, this is the maximum principal stress, and this must be less than sigma allowable. So, this gives one expression from which the value of D could be found out. If the material is again a ductile material, then we have to use the other theory of failure criteria, namely the maximum shear stress. For that purpose, the maximum shear stress tau max is equal to sigma x by 2 square plus tau square. If we use the von Mises theory of failure, then it looks somewhat different. There the equivalent normal stress. So, this is for the maximum shear stress, and this must be less than tau allowable. If you have the von Mises theory of failure criteria, then we can use a different thing. For von Mises theory, we calculate what is the equivalent stress and equivalent normal stress, and that is equal to sigma square plus thrice tau square. This is sigma x square plus tau square. So, this is the equivalent normal stress, and this must be less than sigma allowable. This is von Mises theory of failure. Mises criteria. Okay. So, there are various strategies which could be used, and we have to select accordingly. Now, this is for that case where the distribution is such. If sometimes we have to use different other kinds of distribution, that is, let us take a different thing. We see this is the pin, and sometimes the following distribution is used. Here we have uniform distribution in the middle part, but there we take sometimes a triangular distribution. This is one kind of distribution. Now here also, of course, the analysis remains along the same line. We have to calculate the maximum shear force, and the maximum shear force definitely occurs over here. Again, the value is equal to P by 2, so the maximum shear force is P by 2. So the average shear stress is again the same, P by 2 divided by pi by 4 d pin square, but the moment distribution is totally different, as well as the shear stress distribution is shear force distribution is different. The moment distribution is entirely different, and we have to calculate. Then if you want to calculate accurately using those criteria, that is von Mises criteria or shear stress criteria or principal stress criteria, then we will have to calculate again what is the bending moment first at different sections, what is the maximum bending moment, then we will have to calculate the bending stress over there, and also what is the maximum stress developed throughout this along the length of this pin, and with the help of those data we select the proper dimension of this pin. So this is the way how a pin is designed. Then what remains is the part 2, and part 2 design goes along the same line, because if you open up that part 2, then what you see, the again it looks like the same. But now instead we have here for each fork we have P by 2 load. So here the distribution, pressure distribution is such that this one takes each one, that is, let us consider the top one, this takes a load of P by 2. So this is nothing but P by 2. So each fork here, if it has to break, then the dimension, the sigma, will be equal to P by 2 divided by the area. Area is now, if this is T prime, let us say T prime times the difference, that is D2 minus D1, if we use the same notations. So this is the sigma here. Again it can fail along this line. So this is one way of failure. It can fail by shear along this line. So we will have to use the free body diagram and use the same formula of failure as that of the I bar, which we had already considered. So instead of here instead of P, we have P by 2 all the time, because the net force taken by each of the fork is P by 2. Again it can just crush over here, so the crushing strength has to be checked. So all the three criteria of failure, or all the three modes of failure for the I bar will be same as that of the this fork end. So this is how a machine element has to be checked for failure, and this, using those failure theory, we will have to design the proper dimensions. Here the measured dimensions are this rod diameter, then the pin diameter, as well as the thickness of this I bar, thickness of this fork end, etc. There are other things which are not of importance, that is, say this the roundness, that is the curvature of it. It is important because you see, if there is no curvature here, then lot of stress concentration will be developed, but that analysis is normally not done, and this is left to left to the practice. There are handbooks available. We'll have to always look to those handbooks, and there are standards there. So we'll have to comply to some standards. So in standards, if you see if you look at any of the standards in a handbook, good design handbook, then see that those dimensions, that is the curvature of this I bar here of this fork end, this is related to the measured dimension d. So, this is how normally those things are to be selected. Once this is selected, then of course we can go for further very detailed analysis using various numerical methods like FEM or many other things, and then we can check the safety of the design. But for preliminary safety design, we will have to rely on the theories of failure using proper sections and using the methods described in the theory of failure which were taught in the last classes. So, this is roughly the guidelines for a pin joint design. We will learn many things about the fasteners in the coming classes. Next class we shall study some other kinds of fasteners, which is known as cotter joint, and of course the key joints, and lastly the spline elements. So, this is all for today. We shall continue in the next class. So, thank you very much. Lectures on machine design part 1. This is lecture number 14 and the topic is design of fasteners. This is the continuing part of the lectures on the same topic. Now, in the last class, that is in lecture number 13, we studied how to design a fastener, that is a mechanical joint. Now, in that class we have designed what is known as the knuckle joint, that is the fastener is a pin type joint. Now, we are going to study different kinds of joint today. Mostly we are going to concentrate on a type of joint which uses a mechanical element which is known as cotter. So, let us go to the topic proper and let us see what are the different types of cotter joints. Now, what you see here is one kind of cotter joint, and here you see this part. There are two parts which are to be joined by means of a cotter. Now, this is known as a cotter. A cotter is like a pin, but it has square cross sections. If you want to draw the cotter, then it looks something like this. So, this is a cotter in three-dimensional.